In this video, I'm going to give you a few more examples finding the Maclaurin series of functions that you're already familiar with. In our first example, we have e to the power of x and sine of x. So I am going to do e to the power of x, and I will leave it as homework for you to do sine of x. So we know that the expansion should be a series from 0 to infinity of the terms given by the nth derivative evaluated at 0 and divided by k factorial and x in increasing powers. So for e power x, the first coefficient should be equal to f of 0, which is e to the power of 0. So we know a0 is e to the power of 0, and that is 1. Now, for the second coefficient, we are going to do the first derivative of x, and the first derivative of e power x is e power x again at 0. So f dash of 0 is e power 0, which is 1. So a1 is equal to 1 divided by 1 factorial, that is 1. Now for the next coefficient, we need to do the second derivative, and the second derivative of e power x is e power x as well, evaluated at 0. This is 1 again. So a2 is 1 divided by 2 factorial, and now we can do a3. So for a3, we need the third derivative, and that is e power x at 0. This is 1. So a3 is 1 divided by 3 factorial. So it's very easy to see that the function is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x power 3 plus etc. So if we wanted to write the infinite series in condensed way using sigma notation, we should write the sum from k equals 0 to infinity of x to the power of k, and the coefficients are all 1 over the number of the term factorial, so 1 over k factorial. And so this is the polynomial expansion of e to the power of x. The second example we have is the function ln of 1 plus x. Giving your answer in the form of a power series, we need to find the Maclaurin expansion of the function. So we are going to start finding the derivatives first. So I know that f dash is going to be 1 over 1 plus x. F double dash is going to be, this is the same as 1 plus x to the power of minus 1. So if I use power rule and chain rule, it's going to be easier for me to differentiate. So the second derivative is going to be minus 1 plus x to the power of minus 2. Then the third derivative is 2 1 plus x to the power of minus 3. Then the fourth derivative is going to be 2 times minus 3 times 1 plus x to the power of minus 4, which I can write as minus 3 factorial 1 plus x to the power of minus 4. And with that in mind, 2 times 1 in the third derivative, I can write it as 2 factorial 1 plus x to the power of minus 3. And for the second and first derivative, I can write 1 minus 1 factorial 1 plus x to the power of minus 2. And for the first derivative, 0 factorial 1 plus x to the power of minus 1. Now that I have the derivatives, I will want to evaluate them at 0. So in this case, I'm trying to get all those derivatives and calculations done first so that I can just jump right into substitute in the expression for the polynomial. So evaluating the first derivative, we get f dash of 0 is equal to 0 factorial. Therefore, the first term is going to be 0 factorial over 1 factorial. Then the second derivative at 0 is 1 factorial negative. So the second term, a2, is going to be minus 1 factorial over 2 factorial. Remember that for a2 we need to divide by the counter of the term factorial. Now the third derivative, f third derivative at 0 is going to be 2 factorial. So a3 is going to be 2 factorial divided 3 factorial. And the fourth derivative at 0 is going to be minus 3 factorial. Therefore, the fourth term is going to be minus 3 factorial divided by 4 factorial. Now, I haven't done the evaluation of the function at 0, so let's do that now. F of 0 is ln of 1. That is going to be 0. So my final series is going to start from k equals 1 and not from k equals 0. And it goes all the way to infinity. Of what? I already found the terms. And for the terms, I have 0 in the numerator, 1 in the denominator. 1 in the numerator, 2 in the denominator. The denominator is always 1 more than what we have in the numerator. So, writing it in general, this should be k factorial in the denominator, because they have to match, and k minus 1 factorial in the numerator, and the power of x, which would be x power k. Now, there's one thing missing. Notice how term 1, 3 are positive, and 2 and 4 are negative. So that means that we can actually multiply this by a minus 1, but it has to be such that the even powers are negative and the odd powers are positive. So it has to be k plus 1. So my final answer, and if you want you can simplify this coefficient if you don't want to leave it in terms of factorials, then we are going to get the sum from k equals 1 to infinity of 1 over k x to the power of k times minus 1 to the power of k plus 1. When you have a sequence that changes sign one term to the next, so positive, negative, this is what is called an alternating series. So what we learn from this is that the polynomial expansion of the natural logarithm is an alternating series.